The physics of a rocket moving vertically through the air with angle of attack equal to 0 and no wind force was presented on previous pages. In this section, it will be assumed that there is a perturbing force, and that force we're going to assume is wind. This force acting here at the center of pressure will cause the rocket to rotate about the center of gravity. As a result of this wind force, the angle of attack, and that's denoted by the symbol alpha here, will no longer be equal to 0. An angle of attack not equal to 0 will cause a lift force on this side of the rocket. And this is a good thing. As long as the center of gravity is closer to the nose cone than the center of pressure, this will provide for a counter torque, which will correct for this rotation and move it back in the opposite direction. The net force equation for the angle of attack not equal to 0 scenario is this equation right here. As you can see, this is different than this equation in the following ways. The thrust is now multiplied by this term. This term is an approximation for the cosine of alpha. Okay, and all this is telling us is that when the angle of attack is greater than 0, there is now a horizontal component of force, which means the rocket will go a little bit lateral, okay, in this example here, a little bit to the right, so which means that it will not go as high. Also, this term is now this term. So this constant has gone up with the angle of attack, meaning that the drag force now has increased. You want to design the rockets such that for a given wind force, you want this angle of attack to be as small as possible. The rotation axes of a rocket. There are 3 rotation axes of a rocket called pitch, yaw, and roll. The yaw axis is through the center of gravity in this direction. The pitch axis is also through the center of gravity, perpendicular to the yaw axis in this direction. And the roll axis is an axis through the bottom, through the nose cone, parallel to the body tube. Okay, just as force must be applied to an object to get it to accelerate, torque must be applied to an object to get it to rotate. And we studied this several months ago. Torque is equal to a force times the distance between where the force is applied and the rotation axis times the sine of the angle between the r and f vectors. Torque is also equal to the moment of inertia times the angular acceleration. Applying this equation to torque on a rocket due to wind, let F be the force of the wind. Let R be the distance between where the wind force acts, okay, which is at the center of pressure, a location of Z from the top of the rocket, and the center of gravity, okay, a distance W from the top of the rocket. The angle between the wind force vector and this distance here is considered to be approximately 90 degrees. We know that the sine of 90 is 1. Okay. So dividing both sides of this equation by the moment of inertia, this equation becomes this equation. Okay, so how do you design a rocket to be less affected by a horizontal wind force? So this equation, which we derived on the previous page, provides the answer. For a given torque, this, due to the force of the wind, the larger the longitudinal moment of inertia is, the less the angular acceleration will be. There are a number of advantages to increasing the moment of inertia to minimize this acceleration and the resulting angle of attack, and that is the rocket will fly straighter, okay, so it will have less horizontal displacement, and the rocket will incur less drag. So just a quick review of the moment of inertia, and here I'm going to refer to moment of inertia for the rocket as longitudinal moment of inertia. So it's the moment of inertia about the rotation axis through the center of gravity of the rocket. So here would be out of the page, okay? This was an example I used a couple of months ago when talking about moment of inertia. So the moment of inertia for this dumbbell, I guess you could call it, is this mass multiplied by this distance squared plus this mass multiplied by this distance squared. What this equation tells us is that the further the mass is from the rotation axis, which is here, okay, this distance r1 and r2, the higher the moment of inertia. And since the moment of inertia depends on r squared, doubling the distance of the mass to the rotation axis quadruples the moment of inertia. And then also, the higher the mass, the greater the moment of inertia. The moment of inertia for a uniform cylinder through a rotation axis through the center of gravity is provided right here. And for some rocket designs, this is a pretty good approximation of the longitudinal moment of inertia. So what does this equation tell us? This equation tells us that the greater the diameter of the rocket, or the radius of the body tube, and the longer the rocket, here's L the length, the higher the moment of inertia. So if you really want to create a rocket that will resist a horizontal wind force, you want to maximize the diameter of the body tube and the length of the rocket. Okay, here is an example. Here's the standard Big Bertha rocket, 4.16 centimeter diameter body tube. And I'm flying it in a wind of 10 meters per second. Okay. Here is the same Big Bertha rocket, but I've expanded the body tube to 5 centimeters diameter. And you can see for this given wind force, the angle of attack for the standard Big Bertha rocket was right around 5 degrees. And for the Big Bertha rocket with the expanded diameter is about 4.5 degrees. So certainly this flew a little better in the wind than this rocket did. So as I mentioned before, there are advantages to designing a rocket with a greater longitudinal moment of inertia. Such a rocket will have less of an angle of attack and therefore less of a horizontal thrust component. And here is proof. For that 10 meter per second wind force, the wider diameter body rocket did not displace as much horizontally on its journey to the maximum height. Here it's maybe just a few meters. Whereas for the regular Big Bertha rocket, it displaced something like 25 meters on the way up. So if you recall from the previous simulation you guys did, a wider diameter body tube has greater drag. So even though the 5 centimeter diameter body tube flew better in the wind, it did not go as high as the regular Big Bertha rocket by about 7 meters. A stable versus unstable rocket. A wind or other disturbance has caused the rocket to rotate about the yaw axis. The good news is that if the rocket is well designed, stable, the angular displacement and angular velocity caused by the wind force will induce a counter torque. So what are the design features of a stable versus unstable rocket? Okay, it has to do with the location of the center of pressure and the center of gravity. If the center of gravity of the rocket is closer to the nose cone than the center of pressure, then the rocket will not spin out of control when there's a horizontal wind. The center of pressure is where, on average, the wind forces act, and the center of gravity is where, on average, gravity acts. The stability margin is defined as the location of the center of pressure, Cp, minus the location of the center of gravity, divided by the diameter of the rocket's body tube. The stability margin unit is caliber. So 1 caliber is the diameter of the body tube. The greater the stability margin, the greater the counter torque. But also, the greater the stability margin, which is proportional to that Z minus W that you saw on the previous page, the greater angular acceleration given a wind force. So there's a trade-off. A good rule of thumb for the stability margin is to have it at a level greater than 1 and less than 2. The Big Bertha stability margin is about 1.73. And again, that is the center of pressure minus the center of gravity divided by the diameter of the body tube. Example, stable rocket responds to a perturbing force. Again, we're going to assume the perturbing force is a wind force. Okay, so here you have a rocket traveling upwards and a wind force acts here. This is the black arrow at the center of pressure, causing this rocket to rotate this way. Okay, so as a result of this wind force, the angle of attack, right, is no longer equal to 0. The airflow will induce a lift force, okay, the black dashed line, and it also acts at the center of pressure, causing a counter torque in the opposite direction. Okay, so this counter torque is going to cause the rocket to rotate back in the other direction. The counter torque will oppose the torque due to the wind and slow the rate of rotation. If there is sufficient lift, the counter torque may be sufficient to reverse the rotation direction of the rocket and eventually return the angle of attack to 0. So this rocket is stable because the center of gravity is closer to the nose cone than the center of pressure. Okay, that's the definition of a stable rocket. This is closer to the nose cone than the center of pressure. Okay, what about an unstable rocket? Okay, so again, a wind force acting at the center of pressure. Now the center of pressure is up here. Wind force is the black arrow, causes the rocket to rotate. Okay, it's going to rotate this way now because it's going to rotate about the center of gravity. As a result of the angle of attack now being greater than 0, the airflow will induce a lift force acting at the center of pressure, causing a reinforcing torque in the same direction. The rocket now spins out of control. This rocket is unstable because the center of gravity is further from the nose cone than the center of pressure. Okay, so obviously the lift force is important as it induces a counter torque due to a perturbing wind force. Okay, so this diagram shows the components of the rocket which provide a lift force. And realize that a lift force is only induced if the angle of attack is greater than 0. As you can see, the fins provide the greatest amount of lift. Okay, so the longer the arrow, the greater the lift. The body tube, really not so much. The nose cone, not so much. So here's where you're going to get the greatest amount of lift from the fins. So a good rule of thumb for the stability margin is between 1 and 2 calibers. So how do you design a rocket to achieve that? Okay, so the distance between here and here is at least 1 body tube diameter, okay, and less than 2 body tube diameters. Moving the center of gravity around by changing the material and dimensions of the various body parts. There is a limit to doing this, however, because you're going to have plastic nose cones and body tubes made of cardboard and fins made of balsa. But you can change the dimensions of the body tube, okay? And so you could have a very short body tube relative to a nose cone or relative to very large fins. And that certainly would move around the center of gravity. You can move the center of pressure by changing the dimensions of various parts as well. Realize, of course, that the center pressure of the body tube is at the center. The center of pressure of the nose cone depends on the type of nose cone. Okay, the parabolic nose cone is the center pressure is located at 1/2 the length, so it'd be right about here. Whereas a canonical nose cone is a little further down, okay, from the top, about 2/3 of the length of the nose cone. The center pressure of the fins can be changed by changing the geometry and surface area of the fins. So that's where you can get the greatest amount of change to center pressure because there is flexibility in designing the fins. Okay, so here's an exercise for you. Using Open Rocket, load the Big Bertha original file, fly the rocket with an average wind speed of 10 meters per second, standard deviation of the wind speed of 2.5. That just provides for a turbulence amount. As opposed to a steady wind, it's going to be a rather erratic wind. And then also check the box, use International Standard Atmosphere. So plot on the x-axis position east of launch, and on the y-axis altitude, vertical velocity, and angle of attack. Make a note of the maximum height and the horizontal displacement. Okay, so this rocket's not going to go as high. When you had air with no wind, it went about 212 meters. The fact that this thing is going to have an angle of attack greater than 0 throughout most of its flight now means it's going to have greater drag, which is going to reduce this height some. Okay, so next take that original Big Bertha file and change the fins material to carbon fiber. Okay, so what this is going to do, it's going to increase the weight of the fins and move the center of gravity below the center of pressure. So now it's an unstable rocket. And fly this rocket with the same wind conditions, okay? And make a note of its maximum height, and then make a note, did it spin out of control? And you'll be able to see if it spinned out of control by looking at this graph. Okay, and then 3, just spend some time playing with design, the type of material for the various parts, the lengths and diameters of the various components of the rocket to see how the design affects the stability margin. And then let me know how it flew in the wind. Okay, just provide me some notes. Okay, so turn this in for some bonus points. Okay, so load the Big Bertha original rocket. Okay, you're going to go into flight simulations. Going to edit simulation. Set the average wind speed to 10 meters per second. Set the standard deviation to the maximum, 2.5. And then don't forget to check that box right there. Okay, I'm going to fly with the C6-5 motor. All right. And what you want to plot is you want to plot on this axis, position east of the launch. And on the vertical axes, let's replace vertical acceleration with angle of attack. There it is. Okay, so we're going to plot that. All right, we're going to take a look at it. So here's where it launches. Okay. Here's its vertical velocity. Here is its maximum height. Okay, so as you can see, there's a fair amount of horizontal displacement as it approaches maximum height. Here's where the parachute's deployed, and as you can see, with a 10 meter per second wind, it lands about 700 meters or so from where it launched. That's not good. This is a rocket we will not recover. Okay, so the next thing you want to do is change the fins, the component material, to carbon fiber. Okay, so now you can see the stability margin is minus 0.243. Okay, this is not a stable rocket. So what will happen when you fly this thing in the wind? So go ahead and fly it using the same assumptions as before, 10 meter per second wind, 2.5 standard deviation for turbulence. The stability margin for the Big Bertha rocket before I change the fins is 1.77, as I mentioned before. Really a stability margin greater than 1 and less than 2 is ideal. So this is a very stable rocket. So we would expect this to fly okay, not spin out of control in wind conditions.